Hello everyone and welcome to the first part of our 34th lecture for MAT353. This is the first day of May in the year of 2020, also known as International Workers' Rights Day, so give a thought to the labor movement on this gloomy Friday. We are today going to discuss two major properties of vector fields. These are known as divergence and curl. And while our focus is still on two-dimensional vector fields, because our ultimate aim is to discuss Green's theorem, which pertains to two-dimensional vector fields, these properties are also defined for three-dimensional vector fields. In fact, it can be argued that curl is actually only properly defined when it comes to three-dimensional vector fields. We will work with a version of curl that you might call the two-dimensional version of curl, but its true nature is not clear until you consider three-dimensional vector fields, but those are beyond the scope of this course at this point, and we'll talk more about that in the second part of today's lecture when we talk about curl. Our focus for the first part is divergence. So the concept of divergence is a way of measuring a vector field's tendency to either expand or contract about a certain point. So if we look at our vector field, if we sketch it, as we have learned to do in discussing vector fields, if there is a point where your vector field seems to be pushing away from that point in all directions, as we see here in this picture on the bottom left, that's a point where the divergence of the vector field is positive. And if instead you see the inverted picture where the vector field seems to be converging down or contracting onto a point, so pushing towards that point from every direction, that's going to be a point where the divergence is less than zero. So divergence, the magnitude and the sign of divergence, the sign gives you a sense of the qualitative picture between these two, and the magnitude more of the quantitative measure of how intense is this expansion or contraction, respectively. So for the formal definition, if you have a two-dimensional vector field and if it is C1, again that means both of these component functions have continuous first partials, then we define the divergence of f to be this. So we give it this symbol. We have the nabla, the upside down triangle with a vector hat on it, and we'll talk more about that, and we seem to be dotting it to f hat. This is notational, and we'll discuss that notation presently, but the actual definition of divergence is to take the first component function and differentiate it with respect to the first variable x, and then add to that the derivative of the second component function with respect to the second variable, that being y. So this is the definition of divergence, the partial of f with respect to x plus the partial of g with respect to y. For the notation here, for this nabla hat dot f hat, the idea is that if you take nabla hat to be a vector made out of the first partials, we've been using the nabla to refer to gradients, and so they do have something to do with these first partial derivatives when you think about gradients. If we just give nabla itself a hat, then the idea is that we could maybe make up a vector whose entries are these, what we might call partial differential operators. So for this course and the level of math that we are studying here, we have not formally defined vectors in such a way that I can stick something abstract like the partial with respect to x into a vector component. But it is legal in different contexts. If you work into some more theoretical and more abstract math, then things of this nature make perfect sense. For our purposes now, it can just be a notational shorthand. But nabla hat is going to be a vector composed of the two first partials. F hat is, of course, its own vector with components function f and g, so that when we take this dot product, quote unquote, it's like I'm dotting the vector made up of the first partials to f hat, and thinking about multiplication as applying the operator to the functions here, I end up with this expression. So it does look notationally almost exactly like a dot product, and that's why we like this symbolic representation for the concept of divergence. Anytime you can sort of build the definition into the notation, then there's fewer things for you to remember, which mathematicians are famously lazy, and we like not having to memorize a lot of stuff. So the intuition here is, we talked a bit about it in the previous slide when we thought about expansion versus contraction and what the sketch of a vector field looks like at points where divergence is positive versus points where divergence is negative. Another way to think about it, and one of my favorite ways to think about two-dimensional vector fields, as we have talked about, is to imagine a tabletop or any large horizontal surface and place a small short wall all the way around the edge so that we can add a thin layer of water to the top and it will be held there. So now we've got this plane of a thin layer of fluid, and a vector field might represent the current of the fluid, the direction and the intensity of its movement at each point. So with that picture in mind, if I take a pitcher of water and I start pouring more water onto this table at some point, that water is going to fall, it's going to strike the table, and then it's going to spread in all directions from that point where it enters. And that's what it looks like when you have a positive divergence at a point. It's like I'm looking at the XY plane here as the horizontal tabletop, and right at the origin I'm pouring water onto that tabletop. So this extra water added has to move away from the origin, the point where it's entering the system in all directions. These are what you can think of for, this is a way to think about points where the divergence is positive. And in fact, we call points where the divergence is positive sources. So if you have a point in the XY plane where the divergence of f is positive at that point, we call that point a source for f hat. And likewise, if I take my tabletop that's covered in a thin layer of water and I drill a hole in the tabletop at some point, then the water is going to start rushing towards that hole and out through the bottom of the tabletop. But you would see the movement lines for the water, the current lines, in the sense of the current of a river, all moving towards that point where the water is then rushing out through the bottom of the table. And this is what it looks like at points where the divergence is less than 0, and in fact, we call such points sinks for the vector field. So any point where the divergence of the vector field is less than 0 is referred to as a sink for the vector field. Vector fields where the divergence is 0 everywhere are called source-free. You could think of a sink as being a negative source. That is effectively what it is. And so when we say source-free, we're saying no sinks and no sources. Also interestingly, points where the divergence of the vector field are everywhere 0 are called incompressible. So if you do use these vector fields to model fluids, which they are very often used to do, part of their design was in modeling fluid flow, then incompressible fluids are fluids which would be well modeled by source-free vector fields. Water is nearly incompressible, so you can't really squeeze water down at all. It's not compressible the way that the air in a balloon is, for instance, another fluid. And so if you did build a model of this type, a vector field model for the flow of water, it would make good sense to use an incompressible vector field, a source-free vector field, to model such a fluid, water. All right, let's do an example. So here's an f hat that we considered earlier when we were first talking about vector fields and how to sketch them. Find the divergence. So f hat we have drawn before, it looks something like this. Just based on the picture, I'm going to guess that we've got a positive divergence, certainly at the origin. But even at points other than the origin, I would not be surprised to see that we have a positive divergence. Like at this point here in the first quadrant where my cursor is, hopefully the cursor shows up in the video this time, but right here at about 1, 1 in the first quadrant, there's a little arrow moving into that point, but there's large arrows moving out of it. So the net effect, we would think, would still be to see a positive divergence at such a point. And in fact, if we calculate the divergence of f, we've got this vector of first partials dotted with f itself, and we're just going to get the partial of x with respect to x and the partial of y with respect to y. 1 plus 1 is 2. Here's a sample problem. Take another vector field here. This is yet another one that we considered when we were talking about vector fields. So if you want to go back and review a few lectures back when we were first sketching vector fields, you'll see this is one that we took as an example. I want you to sketch it for me now. So give it a shot first, and then if you need to look back at earlier lectures, do so. Guess what you think the divergence is going to be. Is it positive? Is it negative? Or what else might be happening here? And then find the divergence for me analytically. Alright, you have hopefully paused the video and attempted this problem, so let's have a look. So this is a rotational vector field, is what it was called in the earlier lectures. It actually tends to rotate counterclockwise everywhere. It doesn't really look like things are expanding or contracting necessarily. It looks more like just rotation is happening everywhere. So maybe this is going to be sort of the midpoint between source and sink. Maybe we're actually going to see an incompressible fluid here. And in fact, if we compute the divergence, we will see that we're taking a partial with respect to x of negative y, a partial with respect to y of x. Those are two functions which are constant with respect to the variables that they're being differentiated with respect to, and so we get 0 plus 0 equals 0. This is a source-free or incompressible vector field. So in these two examples, our divergence happened to be a constant. These are two famous examples. We're going to consider them both again when we talk about curl, but one is called radial and one is called rotational. They're sort of perfect examples of what a pure divergence and a pure curl vector field look like. And we're going to talk about those more as we talk about curl. We're going to think about the curl of both of those vector fields as well, and we'll say more about it then. But they're sort of atypical. They're good archetypal examples. We might call them canonical examples of what an all divergence or all curl vector field look like. But typically, in general, vector fields do not have that simple of a nature. You're not necessarily going to see the divergence being a constant. You're certainly not going to see it being everywhere positive or everywhere 0 for most vector fields. So here's another vector field I'm throwing at you. Find the divergence of this one. Where do we see sources for this vector field, and where do we see sinks? I'm not asking you to draw this one, but feel free to attempt it if you like. Alright, let's have a look. So the divergence here, we're taking the partial with respect to x of the first component function, the partial with respect to y of the second component function. We're adding those two partials. I get xy for the partial of the first component function with respect to x. Likewise, I get xy for the partial of the second component function with respect to y, so that those sum to 2xy. Excuse me. So this is our divergence, 2xy. It is not constant. It's going to have a different value for different points, xy pairs in the plane. So where is it going to be positive and where is it going to be negative? Well, it's going to be positive anytime that x and y have the same sign. So if x and y are both positive, or if x and y are both negative, then we are going to see a positive divergence for this vector field. And these two elements, these 2 points, x and y, these two numbers I should say, they have the same sign in the first quadrant where they are both positive, and in the third quadrant where they are both negative. So it's going to be in the first and the third quadrant where these two, or rather where the the divergence of f is positive. Along the coordinate axes where x is 0 or y is 0, the divergence is going to be 0. So it's really the interior of the first and the third quadrants where the divergence is positive. And we see a source for this vector field. So every point in the interior of the first and third quadrant is a source for this vector field. Likewise, the divergence here is going to be negative if x and y have different signs, if one is positive and one is negative, and that happens in the second and the fourth quadrant. In the second quadrant, y is positive and x is negative. In the fourth quadrant, x is positive and y is negative. And so every point in the second or fourth quadrant, more specifically every point in the interior of the second or fourth quadrant, is going to be a sink for this vector field. So that's divergence, a little bit about what it looks like and how to calculate it. As a brief aside here, before we start talking about curl, let's also think about the case where you're dealing with a conservative vector field. So what if f hat is conservative? That always means that it's the gradient of some scalar valued function. So there exists a potential function, little f, such that the gradient of little f is big F. That is to say, big F is given by the first partials of little f. The first component function of big F is little f sub x, and the second component function of big F is little f sub y. So in this case, if we take the divergence of a conservative vector field, we are dotting our vector of partials to the gradient of little f. So we've already got two first partials, and we're taking another first partial with respect to the same variable of each of those. So we're going to come up with the sum of the two pure second order partials as the divergence of a conservative vector field. It's going to be the sum of the second order pure partials of the potential function, little f. And this operator that we designate with a right side up triangle this time around is known as Laplace's operator. If you take triangle of little f, you're taking the second partial of little f with respect to x plus the second partial of little f with respect to y. You can do Laplace's operator in 3 dimensions as well. You will be adding in another second order partial, this time the second order pure partial with respect to z. And Laplace's operator is hugely important. It's not something that we deal with much in this course, but it is of enough interest that we certainly want to mention it when we are this close to it. It shows up as a core component of both the heat equation and the wave equation, two of the most important differential equations in mathematical physics. A great deal of my own research centers on the heat equation, as the heat equation describes how dispersion occurs, how for instance, pollutants might move through the groundwater in the Midwest, near the Ogallala Aquifer. I don't know how to say that, but the big aquifer in the Midwest. So the heat equation and the wave equation both involve Laplace's operator, as does Laplace's equation. And these are all fundamentally important partial differential equations. And we do see that if you take the divergence of a conservative vector field, it amounts to applying Laplace's operator to the potential function, which is interesting. All right, we will return to talk about curl.